All right, I think we're rolling. So, welcome everyone to the Regev Lecture Series podcast. This is episode 3, and the discussion is about amplitude comparison monopulse algorithm in radar. And we have a guest here today, Jorge Ortiz. How are you, Jorge?
I'm doing good. How about you, Nir?
Great, great. So let me introduce Jorge Ortiz. He's a radar analyst and a system engineer. He has extensive experience in the defense industry, specializing in designing and analyzing radar systems with expertise in a range of technologies, including pulse Doppler, FMCW, phased array, and digital beamforming. His technical journey includes signal processing, algorithm development, RF and microwave engineering, and he's proficient in C++ and MATLAB. Currently, Jorge works as a radar systems engineer as a contractor for Saab with NTG, based in Las Vegas. Prior to this, he served as a senior radar engineer at Honeywell Aerospace, where he contributed to the development of advanced radar technologies, notably the IntuView RDR 4000 and RDR 7000 weather radars. His role extended to coordinated flight operations, where he coordinated with flight engineers and pilots on flight test plans and data collection on various aircraft platforms, including the E-170 and AW139. Jorge's career also includes key contributions at Raytheon, where he was instrumental in designing radar architectures for counter-UAV systems and enhancing EOIR platforms with NVIDIA CUDA for GPU acceleration. Additionally, at JT3, he focused on radar system sustainment, always looking for innovative testing and performance evaluation methods. Jorge's academic background is equally impressive, with advanced degrees in electrical engineering from the University of Arizona, complemented by dual bachelor degrees in electrical and computer engineering from UNLV. Whether it's his dedication to radar innovation or his hands-on engagement with the radar communities like the DSP Stack Exchange, where he's very engaged there, Jorge Ortiz brings a wealth of expertise and a commitment to advancing radar technologies. So welcome, Jorge, and as always, this episode will start with an introduction, short lecture about the topic, and this time we're talking about the amplitude comparison monopulse algorithm. So let's have it. Let's have at it. I'm going to share my screen now, and I'm going to present a short lecture and a short intro to amplitude comparison monopulse, and later on we're going to shift over and get the discussion going. All right, so let me go to my website here. Let me know if you can see my screen.
Yep, I can see it.
Okay, great. So inside my website, this is my website, drnirregev.com. Inside my website, there is this section inside learning. In learning, we have courses, books, lecture, and circuit and knowledge. In the circuit and knowledge, there is a free version that contains some of the tutorials and papers, but all of them are contained in the paid version, which is $10 a month, if I'm not mistaken. And inside you have topics like AI and machine learning, probability theory, and so on. This time we're talking about radar theory and amplitude comparison monopulse, so we dive into that. So amplitude comparison monopulse, what is it? It's a widely used radar technique for angle of arrival estimation. And the idea behind it is pretty simple. We look at the relationship between the powers or the amplitudes received in both beams, and the beams are squinted to each other. They have a delta theta or 2 delta theta between them. And let's say that the target is here, closer to the main lobe of the left beam. The power obviously will be higher than the receiving power on the rightmost beam, which will be very, very low comparing to this. The relationship between these powers or the amplitude will be our key metric in evaluating what angle is the target at. and we want to estimate this angle that is called delta theta. This image is taken from a Mark Richards book, by the way. So we have the antenna bore side. The capital delta theta is the offset between the antenna bore side and the actual target angle. L and R patterns are the left and right patterns, respectively, for the beam. And we are summing these powers or these voltages, and we are calculating the difference between left and right. And we call one sigma and the other one delta. And we will see what exactly we're doing with that. So here is a simple MATLAB script that will emulate kind of Gaussian-like patterns for the left and right. And our delta theta here between the beams is 0.15 radians. And that's the beam offset. And we are summing and obviously subtracting left minus right. And that's the sum and the diff pattern. And we plot it here. As you can see, it's like a Gaussian beam. The left one is shifted to the left out of the bore site. The right one is shifted to the right by 0.15 exactly. And now we can see here that I also calculated the sigma pattern, which is the sum, and the delta pattern, which is the difference between left and right. And what do we do with that? So we can prove mathematically, it's not going to be in this lecture obviously, that the delta over sigma is a quantity that is agnostic if we are calibrated correctly. It's agnostic to the phase that the different targets are coming in at, and it's also agnostic to the relevant amplitudes. So the delta over sigma ratio is mostly linear around the center, let's say small angles, and we can use this linearity to calibrate the antennas and the beams such that we have the linearity coefficients here, okay, like the slope, and we can use this slope to predict which angle are we getting the target from. And that's the gist of the ACM algorithm. So the estimated theta is theta naught, which is, let's say, bore site, for an example. And we are calculating the delta over sigma for the powers that we receive, and we're multiplying it by 1 over k, and k is the slope here. Okay, so that's basically giving us the theta angle here on this x-axis. That's why we multiply by 1 over or dividing by k. Okay, k delta is the slope of the linear region. And lastly, without further ado, you can see that here in this MATLAB script, I am estimating the linear trend with polyfit. I'm basically feeding a first order polynomial into this delta over sigma pattern in small angles, and then k delta sigma will be p of 1, which is the first coefficient, the ax plus b. This is the a. And now I test this algorithm. I plug in a true angle of arrival. I get the powers in both L and right antenna or beam, and then I calculate the sigma and delta, and then I just plug it into the formula that we have up here. And we see that for the true angle of 0.075 radians, we get an estimated angle of 0.0751, which is 1 over 1,000 error of radian overall, which is not bad at all. And obviously this changes with SNR, and it changes with the calibration that we're doing, let's say the quality of the calibration that we're doing, and hopefully we're going to discuss more practical considerations during this podcast episode and leverage Jorge's experience in amplitude comparison monopulse. So that is, and then there is a short conclusion, but that's the gist of the algorithm. Let's go back, and I'll stop sharing my screen, and we can go back and start actually discussing a more type of open conversation here with Jorge. So first of all, welcome Jorge, and thank you for joining me in this podcast episode. How are you?
Yeah, thanks for having me. Thanks for having me. It's glad to be here. Excited to do this. I like to geek out over radar stuff, so it's a good
Yeah,
opportunity.
yeah, you and me both. You and me both. So, yeah, I was. Let's start with your background. Where did you grow up, and were any um, experiences that directed you towards engineering, is from childhood or early adulthood?
Yeah, so I'm born and raised in Las Vegas. I mean, I've moved around for jobs, but I was born and raised in Las Vegas. Grew up kind of lower middle class, kind of strong work ethic from my parents. I was born in early '90s, so once I was older, kind of 10 or so, late '90s, 2000s, I got my first computer, and things were a lot different back then.
Yeah,
Um, and with that computer, I got interested in, I had technology in my face for the first time, and I got interested in, well, how do these computers work? I started getting into upgrading them, building them, so all of this introduction to just tech in general started with that first. It was an old E-Machines computer that I had. So that kind of got the ball rolling, just being interested in technology. I think I always had the proclivity for it, but that really showed me, like real technology in my hands, and then that started, the path to getting interested in technology, and then later into, math, physics, and
yeah,
eventually engineering.
nice, nice. So, what inspired you to go specifically to electrical engineering?
Well, it's kind of funny because due to that kind of being around computers, when I got into engineering, I started getting the sense of what it would be like to be an engineer from teachers and the subjects I was starting to learn in high school. So I was getting into, calculus, physics too, which is, in many places, electromagnetics.
Yeah,
So I was like, man, this stuff is really cool. But I was still interested in, like computer logic and
yeah,
electronic design, things like that. So actually, when I decided to go to school for engineering, I actually started out as a computer engineering major. But as I went through that track, I was like, well, I kind of like the heavy double E stuff too.
yeah.
And I said, well, the majors overlap a lot. I'll spend an extra year. Screw it. I'm just gonna do double E as well. So that's
Good.
that's what I did.
Yeah, good. Good for you.
Yeah.
Good for you. Yeah, yeah. Yeah, very cool. Very cool. And did you after you graduated, did you start working or did you do your masters right after?
No, I actually worked for uh, about two years.
Hmm.
So what happened was and this might come up later, but there was no aspect of radar at all in school. A lot of schools don't
Okay.
teach radar, right? There's
Yeah,
only certain schools in the
yeah.
country that really
Unfor-
focus on it.
yeah.
So my first job was actually how I got into radar.
Got it.
And then from there, I was like, well, I really want to get better at this. So that's when I decided to do my master's, which involved a move to Arizona. And then I completed my master's at U of A.
Yeah.
So
And
that's kind of how
and what was your focus there in your master's degree?
my master's degree, well, it was kind of open. I'm one of those heretics that did course only just because
Okay.
I was working full time at Raytheon at the time, and they had offered, hey, you want to get your master's from U of A? They offer a thesis,
Yeah.
a non-thesis option, which I could have done either or, but I know the thesis requires a little bit more of a commitment, and
Yeah.
I didn't want to
Yeah.
stop working.
Yeah.
I was learning a lot there anyway, so I said, yeah, I'll do my master's at U of A. I actually started my master's at ASU
Mm-hmm.
because I really wanted to take some classes from Balanis.
Mm-hmm.
Uh, and I did. I took his first advanced electromagnetics class
Nice.
with him at ASU, but I was going to move to Tucson, so I said, well, it would make sense just to transfer over because I will be at the campus,
Yeah.
so it just made things a little bit cleaner for me. So that's kind of where that transition happened. But I didn't want to go to ASU because Balanis was there. That's why I wanted to go.
Nice.
But U of A again, they're in Tucson area, so they had some radar classes. So I really leaned in more on DSP
Mm-hmm.
and anything radar related. They did offer a radar course in the master's program that was pretty regular,
Yeah.
so I got to take that.
Yeah.
Yeah, so it was more radar DSP, and I did antenna design and microwave as well.
Great. Yeah, that's great. Yeah, I did. By the way, I not a lot of people know that, but my master's degree is actually without thesis as well. So I joined the master's degree, my master's degree, 14 years after the bachelor, and I was already married with two kids at home, two daughters, and they were babies back then, like maybe 3 and 1 year old, and I was doing my master's. Obviously, I was also working, family to support. Someone has to. We needed to keep the lights burning at home, so I did my master's. I started with a thesis program, and then after maybe 1 year into it, we realized that my wife is pregnant with twins, and they're gonna come in like 5 months or 6 months. Yeah. So I shifted my program to a without thesis only courses program, and I took as many courses as I could to finish as faster as I can, because I knew that this is not gonna be easy doing everything all at once, and I didn't want that to impede my grades, because
Yeah.
I once the twins were born, I wanted to devote more time to the family, and less time to academia will obviously impede the grades. So I graduated like that, actually, with a distinction, and they were born, and everything, God bless, went well on this area, on the family area, and I started doing my thesis while working in a radar company. So I did my thesis, just my thesis, for a year,
Mm-hmm.
and then I joined the PhD program, all the way while working, obviously.
Gotcha.
Yeah, so I guess in a way we're kind of similar paths. Yeah, it's I think the masters, which is all courses, and a project, is more suitable for working engineers than
Yeah, and I think that was what was, made me not lament doing the thesis.
yeah,
It's like, I'm gonna be getting more uh, practicality out of the degree if I just take more courses on how to actually do some of the stuff.
yeah, yeah.
Um, so
Yeah, yeah. By the way, I also was exposed to the radar sensing problem on the job, and not specifically, in university. Unfortunately, I think they would gain a lot if they will teach radar as a part of electrical engineering undergraduate program as well. But most universities don't do that, as you mentioned. When you start working with radar, well, how did it make you feel? Like you said, did you feel that this is cool? And why did you stick to radar and not move to maybe in the times that you were engineer, the more lucrative um, business areas for engineers was maybe computer vision or other
right.
sensing modalities, not specifically radars. So what made you stay there?
So at my first job at that company, we support various test ranges in Nevada. So there was a lot of cool stuff going on, and I'm kind of a military nerd, and I actually grew up watching a bunch of documentaries. Actually, my first exposure to radar was I used to watch a lot of World War II documentaries, and they would always talk about the magnetron and
Yeah, yeah,
and what radar did for the British and
yeah,
eventually for the U.S. Pacific Fleet,
yep,
and how that helped. Besides the atom bomb, radar could be attributed to why we won World War II.
yes,
And I was like, wow. And not only that, I'm big on the military, and I was immediately captivated by the sheer potency and asymmetrical advantage
yeah,
that radar systems give our military.
yeah,
And I was like, man, this is really cool. And not only that, the reason I started liking it is because, you know, and I think this goes to your point of why it would be good to teach in undergrad programs, is it exposes you to a bunch of areas of electrical engineering. You got antenna design, you have
Yep.
your RF microwave electronics, you
Yep.
have uh, signal processing.
Yep.
You can even get into like guidance
Mm-hmm.
stuff if you so choose. And then if you're like electronics, there's a lot of things you can do with designing electronics
Yeah.
to fit in those systems. So it really exposes you to a lot of stuff.
Mm-hmm. Mm-hmm.
Um,
Yeah.
and there was just the fact that it was this technology that, and I admit there's a little ego involved here.
Yeah.
I like the fact that it was niche
Yeah.
and that a lot of people didn't really know radar.
Exactly. Yeah. Yeah.
And there's people that know radar at a kind of like a 10,000 foot level.
Yeah.
But when you're asked, like, hey, you're one of two people in this entire place
Yeah.
that knows how this actually works.
Yeah.
Can you do something? That was a good feeling. So that was a part of it too. So besides the technology aspect,
Yeah.
kind of the black magic aspect people see about it,
Exactly.
it's a
Exactly.
wireless technology. People, when a radar is working, you don't really see it
Yeah.
working.
Yeah.
Maybe if it's a mechanical, it'll move and oh,
Yeah.
cool, it's moving. But you have no idea what it's doing and the signals, and especially if there's like electronic warfare stuff going on. I mean, you don't see that stuff, right? And so all of that kind of alerted me and just grip me and never let go.
Yeah. 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 I share the same experience, by the way. So I did early in my career. I started my career in the Israeli military, in the IDF, and then after 6 years I was released, and I went to the industry. And during I think the last 21 years after my military 6 years, I was doing sometimes pure radar work, sometimes pure computer vision work, and sometimes both in the same position, like multimodal systems. And I have to say that I always liked radar better, if not just for the reason that you mentioned, that it's like black magic. People cannot see it. There is no stakeholder that can, like in computer vision, point into a figure on the image and say, why can't you track this moving person? There's nothing to look at in radar, so to speak. And even if they look at it, the maximum they see is a range Doppler map. And yeah, you have to be trained in order to actually understand what's going on there. So it's like they leave you alone, in a sense.
Exactly. And I'm glad you brought that up. There was that dichotomy of the niche field. Not many people do it.
Yeah,
That was alluring, but there's freedom in like, hey, you're maybe one of two guys that knows
yeah,
how to do this stuff.
yeah,
So whatever you say goes.
exactly.
Now,
Yeah,
but that comes with the equal magnitude and responsibility because
yeah,
you better be right because
yeah,
you're the only person. No one else.
yeah,
Again, maybe another guy will double check your work. So
yeah,
it's both. So you get the responsibility that comes with that freedom of, and I like that. I
yeah,
really like that a lot.
yeah, 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 yeah. Me too. Me too. I like it. And yes, it's obviously it's a part of the ego and being proud of what we can do with our engineering training, but also it's a lot of satisfaction, right?
Of course.
This unique position to be in, and I think that radar and this is I think that this is why I also was attracted to investigating microdoppler in my PhD thesis, because again it's like black magic and you can do stuff that no other people can. And even if people know radar, they don't necessarily know a lot of modeling that goes into microdoppler modeling and for target classification and stuff like that.
Okay.
And to this day, I'm still using a lot of it. So, would you say that your, for example, advanced degree, master's degree, pushed your career forward? Your knowledge about?
Absolutely, yeah, definitely. In a lot of ways, because when you're doing the coursework, yeah, you can read the Mark Richards book or Skolnick, and yeah, they'll give you the equations, but it's not the same until you put your hands on the keyboard and say, "Yep, that works," and I
Yeah,
know how to do it. Because sometimes, and we can get into once we start talking about monopulse, yeah, the figures they show you are like here's a monopole slope. If you know your K, you can find the angle. Okay, but then how do you actually do that with the IQ samples you're getting
Yeah.
in the range Doppler map? How do you actually get the angle?
Yeah.
What does it, what does that actually mean?
Exactly.
So for sure, definitely. And actually, it also introduced me to FMCW,
Mm-hmm.
which at the time I wasn't familiar with because I was just working with regular pulsed
Yeah.
radars in that sense too. And not only that, but also got me into looking at FMCW. And then I find that, well, it's actually quite simple. It's one of the most, widely used
Oh yeah.
just because of the benefits that it has.
Yeah. Yeah.
So yeah, but for sure, yeah. My master's degree was invaluable. Also because in my master's degrees I did antennas, and again, this is related to the gamut of my antenna knowledge wasn't quite there.
Yeah.
At least that's my self reflection wasn't there. So taking that antenna course and the RF microwave courses, said, okay, yeah, now I know how antennas work, especially phase arrays, which is usually what I work with.
Yeah. Yeah.
So yeah, definitely for sure. So anyone that what you want to level up in your career, and please get a master's in and take those courses.
Yes. Yes. I totally agree. I felt, and I was in the industry for 14 years before I took my master's. I felt after my master's, I felt that in terms of knowledge and applicability to what I'm doing in the industry, I felt that it's completely changed my level of competency in what I do, and that's remarkable. It's kind of like I felt like I was an engineer, but now I am really an engineer, something like that. In terms of feeling, I can't really describe it well in words, I guess. But it's
I
like
think. I'm sorry. Go ahead.
for me, it was like getting an actual profession, so to speak.
Sure. And I think for me it was the not only the technical, but when you're actually implementing these things, you get that confidence
Yeah,
of yes,
exactly.
I've done it. So it's like having a very sharp sword. You have the sharp sword, but if you're not the confidence, if you're not strong enough to pick it up and wield it,
Yeah,
that's not going to do any good. So you need to have that confidence to say, I
exactly.
know I know I've done this. I know it works.
Yes,
Next time I go to do this, I'll have that confidence too. That lack of confidence won't hold me back in doing the best job. So definitely,
exactly, exactly.
yeah.
And do you think that coming in from the industry to the master's degree, rather than a lot of usual paths, will be continuing right after and staying in the academia without any industry experience, that did this made any difference on how you look at stuff or how you looked back then?
I mean, I can't say for the other because I did work, so
Yeah,
I didn't exist. But I do think it did help having some work experience, just because as you're learning these things, you now have whys behind them, and you
yeah,
have applications that oh, yeah, like this is how I would do this. Oh, that's interesting. Now I understand why this is
exactly.
important. So
Yeah,
that also knowing the whys and the applications
yeah,
also motivates you to
yeah.
learn the subject.
Yeah, yeah, that's exactly how I felt. Suddenly, I understand what I was told to do during the years,
Right.
so
Yeah.
to speak. So to speak,
Mm-hmm.
yeah. Like fully understand. I did my own research, but you can just go as far as without the proper training. I think in a master's degree, like with these courses, really changed how I look at stuff, and
Yeah.
obviously the ability to read more and to understand more books like Skolnick, Richards, and papers. That also was, I think, a big part from due to the master's degree.
Yeah, I think so as well. And also when you read, especially when you're reading texts and papers, because the radar community is so small relative to other fields,
Yeah,
you get used to nomenclatures and language, which can be an issue at times because radar terms get kind of bastardized a little bit, especially since some terms are more legacy, like pulse compression. Like we don't actually compress a
yeah,
pulse, right? Like you know what I mean? Like so yeah. So but yeah, you get used to that language and you get steeped in it, and it trains you to read something right away and know, okay, I know exactly what they're talking about, or I know I can anticipate what they're about to show me,
yeah,
or yeah.
yeah, yeah. Exactly, exactly. So, what when in your career did you actually let's focus now on if you will on amplitude comparison monopulse algorithm. So can you tell the audience about a project that you actually implemented that? What were the challenges? How you go about solving these challenges? Applicable stuff.
Yeah. So my first real application of Monopulse was at Raytheon. We were doing preliminary design for customers. Said, "Hey, we need this capability. Here's," and this is kind of a systems engineering kind of lesson for anyone that's interested. Is you can't just start designing stuff. You need to have the requirements telling you we need to be able to hit this target. It's going to be this big, moving this fast
Yeah.
at these altitudes, because now that you know all that stuff, you kind of start drawing bounds on, okay, I need to be accurate in this domain, I need this kind of SNR,
Yeah.
that kind of stuff.
Yes.
So in this particular case, we had to hit a certain type of target, and we already had an idea for what the antenna would look like. But having, and again, we're working with arrays here most of the time. So, and you mentioned in the lecture, you start saying, okay, well, we know we're going to be able to get these SNRs just off, our waveform. Let's start looking at what our antenna pattern looks like. Okay, great. This is what the antenna pattern looks like. Let's start playing around with our monopulse. So in your lecture, and you kind of went, we went quickly over it. There's that squinting of the beams is important, because there's a trade-off. Is you can squint and make your pulse really tight, so you're much more accurate. And you can look at the literature, the expressions pop out where, the accuracy of your angle is based on SNR and your K.
Yep.
Bigger SNR, bigger K, more accurate.
100%.
But the problem with making your slope steep is that now the range of angles that you're linear is smaller.
Yeah.
So there is that trade-off of, well, you want to be able to resolve a target in as many angles as you can.
Yeah.
But you can't buy that, because you're gonna lose. You need that accuracy too with the tight slope. So there's a trade-off there. So you start playing around with, well, if our SNR is high enough, can we just get away with just splitting the array in half evenly? Whatever those sum and differences look like, is that good enough? And you do your analysis on quick simulation. Hey, I have this target moving. Yep. How close can I get to the angle? And you're like, hey, this is good enough. Let's keep going. And if it's not, then you start playing around with other stuff. So that and that's why radar is interesting, because maybe the antenna, you're doing the best you can do.
Yeah.
But your SNR sucks. You're like, well, now I got to look at my waveform. And
yeah.
So that project, that the monopulse, in our particular case, we didn't have to get too fancy with it. It was a nice, even, and you'll see it a lot classically, though, when you're take some courses, you'll have like a planar array. They'll just do 4 quadrants, and that's usually many times good enough. I mean, monopulse is very accurate, but there could be times where you might want to play around with how you squint, especially when you scan, because as you scan, your beam pattern changes.
Yeah.
So your K will also change.
Yeah.
And now you have to say, well, how does that work? And then you have to kind of parameterize. Okay, well, for my array steering angles, are my beams still good enough to even do monopulse? So yeah, there's a lot of cool trade-offs you do.
Yeah.
So we did a lot of that initially, but it was pretty quickly resolved. Doesn't take too long if once you kind of again have that confidence that you know what you're doing, and said, yeah, the array is good. It does what we want it to do. It's accurate enough. Our SNR is good, and okay, here's K. Obviously, K will change as you steer. K will change with temperature. You got to be able to calibrate.
Yep.
Things like that. But yeah, that was the first. No kidding. Now, I was exposed to monopulse before that project, but it was already in an existing legacy system that did it differently. It used a single antenna with a very special type of feed that would produce the sum and difference for you. So that's my first exposure, but my first actual implementation of it and doing analysis on monopulse on a real system, real hardware.
Yeah.
was at Raytheon for that particular preliminary radar design we were doing.
Got it. And was it digital mainly, or was it
Yes,
analog circuits that are
it
doing
was
the sum and difference?
it was digital.
Digital. Yeah. Yeah. Makes sense. And from your experience, how uh, I call it a super resolution technique because it can, in my experience, it can produce 1/10 the beam width, at least. Do you have the same experience in terms of precision? I mean,
Yeah, no, we were getting. Yeah, I think that's. I think even better at times
yeah,
if the scenario is correct. But yeah, I mean, super resolution kind of gets some people upset
yeah,
when
yeah.
you mention the term because there's other techniques that people call super resolution. But I agree in what you're saying is that in terms of the precision you can get off the measurement,
Yeah,
yeah, I mean it's very very accurate.
yeah, 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 yeah. I know I kind of maybe at times I don't do justice to the term super resolution, but that's how I call it, so people will understand what I'm talking about. Like people who are not radar practitioners. So we can think about monopoles as a sort of sophisticated way of interpolating, right?
Yeah, I'm trying to maybe I'm trying to see what you mean there, interpolating in terms of like the beam space of the.
I mean like for example when we do sometimes when you do even in pulse Doppler
Mhm.
or FMCW when you get the range profile in FMCW it's after the FFT and pulse Doppler you just get after the cross correlation you get the range profile and you take the maximum or you do a CFAR detector and you take the target and you don't just you're not satisfied with just the bin type of precision, right? You do interpolation between bins,
Oh, gotcha. I see what you're saying. Yep.
and here we're doing some sort of interpolation, even a linear interpolation, so to speak, between two beams, right?
Right.
Between the ratios or the relationship between two power levels in these two.
Gotcha. I see what you're saying. Yes. Yes. No. Agreed. And just like some history. Monopulse is quite old. It's been around for a long time. But when it came about, it was considered extremely high tech, just because we were used to doing like conical scan.
Mm-hmm.
You had to actually mechanically move the beam around, and you were dependent on target amplitude, which is exactly what the monopulse technique
Yeah,
makes it agnostic. So it's not as easy to jam. It's more stable.
yeah,
Um, so
yes,
yeah, but I see what you're saying. You can interpolate within that
yeah,
angle range. Usually the main beam is what you're concerned with.
yeah, exactly,
Yeah.
exactly, exactly. Cool, cool. Yeah, very cool. How do you go about like practically? How do you? What's your protocol on calibrating and recalibrating in order to make the actual algorithm to work? Otherwise, K will not be accurate and you will be thrown off, right?
Gotcha. So with a good calibration routine, you well, number one, like at the system side, you you get your specs from the front end guys saying, hey, the antenna and the receiver looks like this, and it changes this much with temperature. We don't expect you know this type of change in amplitude to occur within, I don't know how much time they give you.
Mm-hmm.
So you say okay, and then you design a periodic or sometimes on demand calibration routine where you sample yourself. You say, hey, are my phases in line so that I can form the beams? Now, we were blessed because we were at Raytheon with a lot of factory characterization was very good. So they did a really good job at saying, well, we've tested the array and the electronics over a lot of wide temperatures. Here's what the dB and phase change looks like over temperature for each receiver. We don't expect it to go beyond these bounds. And using those bounds, you say, okay, well, now I know how often I need to calibrate. And then as you're sampling yourself, you can say, oh, I'm in a degraded state.
Mm-hmm.
Do an on-demand calibration.
Yeah.
Or sometimes you're like, I'm on a degraded state. Half my channels are gone. do something else. Maybe you'll change your squinting, or sometimes it's just a total failure. Like, hey, somebody blew half your array away. You're done, right?
Yeah.
But definitely just a solid calibration routine. Because really, when you're calibrating, you're saying, can I form a good beam? And if you can form a good beam, which includes everything from the antenna to the electronics, if you can form a good beam, you will have a good monopulse.
Yeah.
So as long as you can prove to yourself, yes, I'm forming good beams, I'm confident in my subsequent calculations.
Yeah. In terms of, I sometimes I encountered the monopulse in actually two pulses, one looking right, one looking left. Do you have the same experience, or when you did it, it was always the same pulse,
It was always the same pulse.
which is the better approach.
Right.
It's
You're
more,
referring more like the sequential lobing type,
yes,
where
yes,
you're
yes.
right.
Kind of force sequential lobing to be a monopulse, so to speak. Like use the
Right.
same algorithm for that, but with a sequential lobing of two.
Sure. And that's what's cool about monopulse is once you get past the antenna beam forming stuff, everything is pretty much the same to
Yeah,
actually get the angle. It's so you really have to know, besides just the math and the DSP, aspect of monopulse, you have to understand, hey, what is your antenna doing? So you really have to have some chops in your antenna
yeah,
and your beam forming
right,
theory to know, okay, this is how I'm doing this, or hey, my system's half, it's some of it is analog, some of it is digital, maybe it's fully digital. You really have to understand how that's happening. But it's nice that once you get past that point, you're okay, cool. It's the same calculation. You have your slope, and you're good. Yeah,
yeah.
yeah,
That's true. Very simple, very simple.
yeah,
Yeah, that's also cool about radar stuff, right? Sometimes the algorithms are so simple. It's like if it's not simple, it won't work. Of type of a, I would say, state of mind when you design stuff. Even in
right.
sophisticated trackers and other stuff, we tend to keep it very simple. We want to.
Yeah, yeah,
Yeah.
yeah. And it's funny you mentioned that, because I think that's part of the I liked about it too, is that when you're reading the theory, you're reading the text, man, there's pages and pages on describing what it's doing, the math, and then you get to implementing it. It's like, this is 3 lines. Like,
Yeah.
this is,
Yeah.
it's
Exactly.
yeah, you're like, it's 3 lines of code. I mean, there obviously there was a lot that went into it,
Yeah.
but the actual implementation is like, wow, this is actually quite straightforward once you know what you're doing.
Yes.
So
Yes.
so that collapse of like, wow, all this knowledge just collapses into this nice little thing
Exactly.
that works
Yeah.
is
Yeah.
is really nice.
Yeah. It's like you have to have all this knowledge in order to collapse everything to something very simple that works, that actually works. And
Yeah, and that's the satisfaction part of it that you were referring
yes,
to earlier, where like, wow, all that knowledge that I use really did work, and here it
yeah,
is, and,
yeah,
and it
yeah,
works. Yeah,
yeah.
yeah,
It's actually estimating the angle. Yeah,
right,
yeah,
exactly, yep.
yeah. It's amazing. It's amazing to me. You know that in lidars they don't have it. They point a very narrow beam to a known angle, and that's the angle they report, and that's
Hmm.
it. And they scan like this. It's not like we have it in radar. I worked on a very interesting FMCW lidar project in up to maybe 4 months ago, 5 months ago. I was working on it for, I think, something like 3 years, doing all the DSP there. There is no angle of arrival type calculations.
Right. You just point and you say, well, my beam is so small,
Yeah, that's the
I can,
elevation,
yeah.
that's the azimuth, that's it. Everything else is like radar theory, but that's the range, for example, is like radar theory. But the rest is where the beam is pointing. And there is no super resolution beyond the beam resolution.
But you can't see us far, so
No, they can't.
yeah,
They
right,
can't. Yeah, they can't go through walls as well. Yeah.
right, exactly,
Yeah,
yep.
yeah. So in your current position, are you still? It's the company that you're working for. Is it also government type aerospace defense company, or?
Yeah, it's Saab. So
Yeah, yeah.
Saab Inc., based out of Syracuse. Yep.
I see. Yeah, yeah. I know Saab for being a automotive company. That's why I asked.
Yeah. A lot of people always ask me like the cars. I'm like,
Yeah.
well, Saab actually, the history of Saab, they were They were, the Swedish, the big Swedish defense company.
Yeah.
I think they started before World War II, if I'm correct. I don't remember their, but they have, they've been around for a long time. It's just that in North America, they got into the car business a little
Yeah.
bit, and then
Yeah.
people always say the cars, like, no, it's, Saab, and it's kind of funny because Saab actually does a lot of known products
Hmm.
that unless you asked or knew, you wouldn't know it was Saab.
Yeah.
That did them. So like the Carl Gustav and like the AT4 munition launchers. Those are Saab.
Yeah.
The Gripen aircraft is Saab, and a lot of radars are, especially for the Navy right now, are with Saab.
Yeah. Yeah.
Yeah.
Yeah. So are you're probably staying on top of the current radar trends, right? How do you do that? You read papers, you go to conferences. How do you stay on top of everything?
Well, I think when I was at Raytheon, a lot of the challenges, we get through reports of like, hey, this is what's going on with a customer would say, hey, these things we're worried about. So kind of with those con ops that they start bringing at you, you
Hmm.
start thinking about, well, does our current tech handle that? Does it not? So a lot of times the trend is kind of unknown. You know what the problem set is, but you don't really know. Okay, how are we going to solve that?
Hmm.
And sometimes it is a radar specific technology. Sometimes it's a strategy. Like a tactical strategy. Maybe instead of making one really nice radar, you really need two or three or four systems. So yeah, I mean, I think a lot of just customer interaction gives you a lot of good insight into, because it's a customer, right? So they're
Yeah.
telling you, we need this, we don't have it. So you kind of get the answer. But recently I've been kind of keeping up with the trends, and we're going into things being automated. So specifically, self-driving vehicles, and now automated commercial uses like automated uh, livery aircraft.
Yeah. Yeah.
And they're interested in, well, GPS navigation isn't good enough. We need to have sensors on there to detect other things, especially with the proliferation of drones.
Yeah.
Um,
Yeah.
how do we do that? Well, hey, there's a solution called radar that will work just great.
Yeah.
And then also, so there's that problem space of, oh, the commercial sides. Besides, you had a weather radar that was
Hmm.
been a commercial thing, but it was very
Right.
niche to.
Right.
But now that we're getting into more commercial uses, and
Hmm.
people are kind of discovering
Yeah.
radar in a sense.
Yeah. Yeah.
And so it's a good thing that radar is getting a little bit more proliferated, but there's also the negative aspect that a lot of people, there's a lot of misunderstanding about radar, how it works,
Oh yeah.
and that muddies the water when
Yeah.
you have discussions
It does. It does.
with people that are trying to get into radar.
Yeah.
And for example, I might get in trouble, but like comms guy, they love calling like a phase array a MIMO system, because because it's a comm term, right?
Yeah.
But
Yeah.
but phase arrays, we don't call them MIMO systems
Yeah.
as
No.
radar engineers, right? So when people, so those are the kind of things that you kind of struggle with,
Yeah.
and someone trying to learn radar now, you might be led astray in certain, depending on where you're looking,
That's true.
just because people use different terms and their misunderstanding isn't quite there.
Yeah.
So just be careful for anyone that's getting to radar. My bias, because radar is a defense technology, stick to defense sources on what radar is, and you'll
Yeah.
be better off.
100%. Yeah, I also come from this. But by the way, when I moved to the States, I was sure I wouldn't find any project or a job to work on in the radar realm because I didn't have a clearance. And I
Hmm.
couldn't get a clearance because when I moved, I wasn't a citizen, an American citizen. So, but I guess I was blessed in a way because then in 2016, 2017, the boom of miniature radar started. And now my company Aleph Zero, we do projects for inside the house, outside the house, inside the car, outside the car, delivery drones, what have you. And not only for defense. Actually, most of what we do is not. All of what we do
Yeah.
almost is not. So it's everywhere radar now. It's going into baby monitors. It's going into
Hmm.
inside the cabin in cars. It's going into security systems outside the home. It's going into inside the home elderly care and sleep
Yeah.
tracking.
Medical devices. Yeah.
Yeah,
Yeah.
yeah, medical devices. Yeah, absolutely. Robots that they use radars now as sensors. Also for SLAM, also for localization. So
Hmm.
what you just described is, I think, that radar is becoming more and more ubiquitous, and that's, I think it's good, because maybe that will force the academia to understand that they're missing on something here.
Yeah. I agree completely.
Yeah,
So anyone that wants to get into radar, it's a good time because
it is.
historically back World War II, Korean War, Vietnam, you had a lot of people getting into radar because it still is again
Yeah,
the black magic. Not many people know it, but it was a little bit more, I guess, pushed back
yeah,
then,
yeah,
and a lot of those people are retiring now.
yeah.
So there's not a lot of radar guys out there.
Exactly.
So if you want
Yeah,
to get into it, it's a
that's the
it's
right
a
time.
you're yeah, it's the right time. and
Yeah,
and
yeah,
and by the way, the commercial side will need the help because they definitely need the expertise, and you'll be in a good spot to get
yeah,
in there.
yeah. 100%. I agree. And all these stuff that I have here, these are radars. It's amazing to me. When I worked on radars, it was yay big.
Hmm.
Even bigger. And now it's all like tiny semiconductors. Everything is the same. Just smaller antennas, smaller footprints. The theory behind it haven't changed. It's
Nope.
the same signal processing chain, same, exactly the same. It's just amazing to me how far we've gotten with radar, and how what's the potential in radar. People also call it radar vision or radar imaging now, but there is a lot of potential there to innovate. Also, AI is introduced into radar. I actually have a course on AI and radar signal processing through my website. People that wants to know also machine learning, deep learning, AI, and also radar. Why not? Why not combine the two?
Yeah.
And that was my approach, at least, because I'm I love math, I love engineering, and I try to combine stuff from these different disciplines. So AI and radar, machine learning, deep learning, it's going to be there. Um,
Yeah.
yeah, I mean, I'm not sure to what extent, but for target classification, 100%, it's
Yep.
going to be there. Why not?
Yep.
It is there already in some places. I know it for sure. So yeah, this is an exciting times for people to understand and learn about radars, especially if you're a, a electrical engineering student. So what kind of advice would you give the nowadays current students of electrical engineering?
So just a general electrical engineering or radar specifically?
A general. Let's assume that
Okay.
most of them don't do radar.
Yeah.
Yeah,
Okay. So number one, just accept and appreciate the fact that electrical engineering is tough.
yeah.
Okay, it's probably one of the toughest things you can learn.
Mm-hmm.
So if you're struggling with a certain concept,
Mm-hmm.
don't don't take it too badly. It's something we all struggle with. If you might have classmates that seem like rock stars, but trust me, there's something that they'll struggle with too. So
Yeah. Yep.
you might be better at it. So don't keep your head up.
Yep.
It's hard for a reason. That's why there's not that many. I mean, there's a lot of double E's, but I'm saying in terms of
Yeah.
all the other fields you can go into possibly. There's a reason that there's not that many of us. The reason it pays well because it's hard.
Yep.
So once you're doing it, just say, hey, I'm struggling, but
Yep.
keep going. And also with that though, you do have a responsibility to yourself to really understand the concepts because you can't get away with cursory looks at some of the theory. You really
Yeah.
have to know what it means. You might get away with it for a while, especially in your first, second semester. But once you get to your senior year, if you don't have those concepts down, it's going to kill you. And especially if you somehow get away with it and you graduate, it's not going to go well for you in industry.
No.
So really pay yourself now by, doing the work, blood and tears.
Yeah.
You will thank yourself later.
Yes, blood and
But,
tears. Yeah, that's what I tell my students. That's the, I think, I mean, to me, is at least from my observation, it's the hardest. It's the hardest field to study, maybe in the world. Which, first of all, when you graduate, it makes you feel awesome because now, if you want to study another profession, you can do that easily because you have the tools
exactly.
now. And it's so multidisciplinary that it's involved math, physics, mechanics. Depends on where you're going. You will find yourself doing mechanics, dynamics,
Right.
physics. I used to design trackers to various targets. So you have to
Mhm.
understand the dynamics of targets and so on and so forth. So it's a lot of this stuff. Probability, stochastic processes is there, detection theory, estimation theory, everything is there. And if you don't invest in that, you will be a mediocre. Maybe you won't advance in industry as you might if you actually invest and just sweat it out. Sweat these 4 years
Yes.
out, and you'll
Yeah.
thank yourself later. Exactly as you said. I
Yeah.
100% agree with that.
Yeah.
100.
And like you said, the skills you'll learn as a double E, just because of all the hard work, your mastery of physics and math that you'll get
Yes.
with it.
Yes.
If you want to get into another tangential field, it'll be a lot easier than the other way around.
Yeah,
No
yeah,
doubt.
very easy, very easy, very easy. Yeah, it's almost it's unappreciated until you see it with your own eyes. I used to work for a company when I got here. I used to work for a company for they closed the U.S. offices a year after I moved, so I was kind of fired and was forced to weigh here with my company
Hmm.
Aleph Zero, so to speak. But I used to work for this company who had a legal counsel coming from another state in America to California, and uh, this individual learned for the bar exam because you have to qualify in each state when you move.
Right.
I guess they were already lawyers, but they have to do the bar exam for the specific state. In this case, California,
Hmm.
and they failed. And I approached this individual and told her, uh, "Give me the books. Give me 2 weeks. Like close it with my bosses. I'm taking the bar exam and I can pass it." And what makes you think I'm an EE? I can learn anything, And it's not just ego speaking. It's an actual experience that you can do tough stuff. That's what, in terms of learning and the ability to learn new concepts and to grind through the frustration that you get when you don't understand
Exactly.
anything. That's
Exactly.
that's very prevalent when you're studying electrical engineering, that you don't understand stuff, and unless you're a Gauss or a Newton, that's the feeling you will get when you go through the motions of becoming
Right.
an electrical engineer.
Right.
And I'm no Gauss and I'm no Newton, so I got this feeling a lot during my
Yeah.
master's degree, bachelor's degree, as well as my PhD. And your ability to go through these obstacles, I think it's what makes you better at what you do. That's my experience, and also I draw the equivalence, and I tell people this is the Navy SEALs of engineering, electrical engineering. So if you go there, invest yourself in it because it's going to pay out.
Yeah, absolutely. And it's funny, a quick example, it's actually related to the legal thing. I know a few people who did their undergrad in electrical engineering and then went to law school and they were accepted like that.
Yeah,
Because even some other schools, like law schools, understand
yeah,
the type of person that can do an engineering degree, specifically electrical engineering,
yeah,
and say, yes, that is a person that can learn law.
yeah.
So
Exactly.
so so yeah. So just keep that in mind that you get a lot more out of a double E degree than just the theory of being a double E. There's other ancillary stuff that will help you out in
Yeah.
other fields, and quite honestly, in your life, you'll learn some character, get a little grit with all that pain and suffering that you're going to have for 4 years, but
Exactly. Yeah.
it pays off.
Exactly right. Exactly right. Yeah. It strengthened the character for sure. Jorge, just before we close, what is your, if you can share with us, what is your plans for the future as you evolve in your career?
Well, I'm working towards once I get a bit more established, I'm still kind of considering some things. I would like to cement myself as a kind of baby step would be fellow at some organization to really lead radar designs for whoever needs the help, and establish a legacy of these radar systems were designed and led by myself, and have that be known, and
Nice.
be a source of expertise, not just to the organization, but just to the entire radar community as a whole. So I'm still pretty young, relatively speaking, so I still got a little bit to go, but I think
Amazing.
I'm working up to that. So
Yeah, amazing. Amazing. That's a good thing to work up to. Yeah, there is so many opportunities in engineering and in electrical engineering, so many avenues one can take, and I think you can actually, everyone has a place to carve their own path in this, to me, fascinating field, and to successfully make an impact like you are doing. And it's noticeable to me that you are doing it as we speak. And there is no doubt in my mind that you will succeed in what you just said. And
I appreciate that, Amir. Thank you.
yeah, and thank you, Jorge, for devoting your time and joining me on this very interesting conversation. And I hope to have more in the future
Yeah,
with you.
yeah. Thanks for having me, Amir. Appreciate it.
Absolutely, absolutely, my pleasure. All right, brother. Until then.
All right,
Bye bye.
sounds good. Yep. Bye bye.